This is the fifth section of chapter 1 on number theory, and this is on solving congruence equations. Now, in some ways they're similar to normal equations, and there are some differences as well. The first thing to note is about the number of solutions. Now, we may have congruence equations that have no solutions, one solution, one unique solution, or they may have many solutions. Now let's look at the ones where we have either one or many solutions. Those solutions are positive, so you won't get any negative solutions, and those solutions are always less than the modulus. Now, the name we give to this, these solutions that are written like this, they're called the least residues. And we would want to write our answers in that form, the least residues. Okay, you could think of residues like remainder, and you'll see that when we go through some examples. Actually, I'll do an example here. So if I had this modulus equation or congruence equation, so x is congruent to 12 mod 5. The least residue needs to be less than 5. So all I'm going to do is I can take off multiples of 5, keeping them positive until this becomes less than 5. So if I took off 5 from that, I'd get 7. That's still greater than the modulus, and take off 5 again, I get 2. So actually this equation would be x is congruent to 2 under mod 5. So this 2 in this example is the least residue for mod 5. The next thing with modulus equations is that we can add or subtract the same thing from both sides without doing any further work. So add or subtract the same thing from both sides, just like you would in a normal equation. So here's an example. So let's say I had x minus 10 is congruent to 4 under mod 8. Then I will just add 10 to both sides. I can do that, no problem, I'm allowed to do that. So x would be congruent to 14 under mod 8. I would need to change that solution to a least residue solution. So I take off multiples of 8. In fact, I only need to take off 1 8 to get to 6. So that will be the solution for that equation. So we can add or subtract the same thing from both sides. Now we're going to be looking at equations which are in this form. Ax, so something times x, is congruent to b under mod m. And by working out the greatest common divisor of a and m, whatever those two numbers may be, we can work out if the equation has any solutions and how many solutions it has. Okay, so if, for example, if the greatest common divisor of a and m in this equation, if that divides b, then there are solutions. So I'll say solutions exist, and the value of that, so once I've done the greatest common divisor of a and m divided by b, I'm going to get a number, let's call that d. The value of d gives the number of solutions, so the value of d gives the number of least residue solutions. However, if the greatest common divisor of A and M does not divide B, so the greatest common divisor of A and M, if it does not divide B, then there are no solutions. So we can use that as a check to see whether an equation has solutions or not, and if it does have solutions, how many there are. So here's an example. Let's say I had 9x is congruent to 5 under mod 18. So first of all, I work out the greatest common divisor of 9 and 18, which is 2. So I see if this 2 divides B, this value here 5. 2 does not divide 5, so that means this equation has no solutions. If we try one like this though, let's say we had 12x is congruent to 20 under mod 8. Yeah, mod 8. So we work out the greatest common divisor of 12 and 8. That is 4. So we see if 4 divides 20. Yes, it does. 4 divides 20. And the 4 then tells us the number of solutions since it divides 20. So this tells us that this modulus equation, there will be 4 solutions, 4 least residue solutions. Okay, next we're going to be looking at equations where both sides can be divided by the same number. Okay, so equations where we can divide both sides by, and let's call this value we can divide both sides, we'll call it k. So that means the equation will be able to be written in this form: something times a and the same thing times b mod m. So the first thing we need to do is we need to work out what the greatest common divisor of these values of k and m are. And if the greatest common divisor of a and m is 1, which basically means that, sorry, not a and m, k and m is 1, it means that k and m are co-prime or relatively prime, then we can just go ahead and divide both sides by k. Divide both sides by k, and we'll keep the modulus the same. So it will still be mod m. However, if we work out the greatest common divisor of k and m, and it doesn't equal 1, let's say it equals some value that we're going to call d. So we work out the greatest common divisor of k and m, and it's some value which we'll call d. Then we still divide both sides by k, but we also need to make sure that we divide the modulus by d. So the question now becomes mod, and I'll write this as m over d. So in the first example, where the greatest common divisor of k and m is 1, they're co-prime, then you just divide the equation, you leave the modulus unchanged. If the greatest common divisor of k and m is not equal to 1, it's some value called d, we divide both sides by k and we divide the modulus by d. So here's a couple of examples. So let's say I had 14x is congruent to 42 in mod 5. So the first thing that I would do is work out the greatest common divisor of 14 and 5. Okay, which is 1, which means that the 14 here and the 5 here are relatively prime or coprime, then all I do is divide both sides by 14. So I should have said that the 14 came from the value that I was going to divide both sides by. Yeah, I can divide both sides by 14, so that's where the 14 here came from. So I'll just go ahead, divide both sides by 14. So I will get x is congruent to, so I think this is 14 times 3. But the modulus stays the same. It stays as mod 5 because this value here was 1. Okay, let's try one where maybe the greatest common divisor is not going to be 1. So let's say, for example, we have something like this. 10x is congruent to 70 under mod 15. Right, so I'll make it a bit clearer this time. So I want the greatest common divisor of what I can divide both sides by. Now here it happens to be 10. Now it's not always the number that's written here, it just happens to be in my examples. So I can divide both sides by 10. So I want to find the greatest common divisor of that and 15. That is 5. Now what that means is I still go ahead and divide both sides by 10, like this, but then I divide the modulus here by 5. Whoops, not actually right 5. So that will now become mod 3. Now, once we write that as a least residual by taking off multiples of 3, so take away 3, we get 4. Take away 3 again, we get 1. That will give us one solution, but we can go all the way up to the modulus of the original question. So we can go solutions or residues, not residuals, residues all the way up to 15 by keep adding 3 to the 1. So we've got 1 plus 3, 4 plus 3 again, plus 3, plus 3. If I plus 3 again, I go over the 15. So actually there are 5 solutions here in this equation. And it happens to be the same as that one. I think there's a connection between the two, the number of solutions and the value we get here. Okay, so this leads us on to the last rule, or last thing that we can do with equations. So we've looked at adding and subtracting, we've looked at dividing both sides. So the last step here is going to be where we multiply both sides, multiplying both sides, but we actually multiply both sides by something called the multiplicative inverse. The multiplicative inverse. Now we're going to know when to use the multiplicative inverse because we are going to have equations that look something like this. 5x is congruent to 7, let's say under mod 30. Now the problem with this is that 5 and 7 do not have a common factor, so we can't divide, but we can work out what to multiply both sides by. So this basically becomes x is congruent to something. So if we were to call the number that's here a and this b and the mod m, just like before, we're going to start by finding the greatest common divisor of a and m. And if that's equal to 1, and only if it's equal to 1, we can find the multiplicative inverse. Now you may recognize this from when we use the Euclidean algorithm and Béziers identity. And what we do, once we've found that the greatest common divisor of a and m equals 1, we'll use Euclidean algorithm followed by Béziers identity. Let's spell that right, identity. Then that will allow us to write 1 equal to, and we'll write it in this form, AP plus mq. So a is just this value here. The a that comes from here, m is going to be the value of the modulus, and the multiplicative inverse is a. Okay, a little bit of space here. So p is the multiplicative inverse. P, the value of p that we get after doing the Euclidean algorithm and Buse's identity, the value of p, that is equal to the multiplicative inverse, and this is what we'd multiply both sides by, and then we'll be able to solve the equation. Right, so we'll start with a nice easy one. Solve the equation x is congruent to 86 mod 7. So all we need to do in this question is write the least residue of 86, or the least residues. There may be more than one. So what we do, we're going to do 86 and we're going to subtract multiples of 7 until we are below 7. So I think if I took off 70, I'm down to 16. That's still too much. Take away another 7, that's 9. Take away another 7, that's 2. So x is congruent to 2 in mod 7 would be the least residue solution. Okay, in this one, we want to solve the equation x plus 15 is congruent to 3 under mod 10. So remember, we can just simply add or subtract to both sides without making any changes or using any special algorithm or anything like that. So the first thing we'll do is just take away 15 from both sides. So that'll give me x is congruent to negative 12 in mod 10. I need a least residue solution. This is not a least residue because it's negative. They must be positive. So if I add multiples of 10, so if I add 10 to that, I get negative 2, which is still negative. Add another 10 to it, and I get 8. So x is congruent to 8 in mod 10, so that will be the solution to this equation. Okay, in this example it says explain why this equation has no solutions. Now the way that we check to see if an equation has solutions or not is we need to work out the greatest common divisor of a and m. So the greatest common divisor of 14 and 22, that is 2. Now for there to be solutions, 2 needs to divide b. So this is the value of b. So let me just put, this is like ax is congruent to b mod m. So these are where the letters come from. So does 2 divide 7? And the answer is no. So we'd write since 2 does not divide 7, the equation has no solutions. No solutions. And that will always be the case if the greatest common divisor of a and m is equal to 2 and that doesn't divide b, there won't be any solutions to the equation. Okay, so this question here says solve this equation. So we're assuming there are solutions, so we don't need to check whether there are solutions or not. But I can see from this question that I want to divide both sides by 2. Okay, that's what I want to divide both sides by. So you can think of k being 2 in this example. And I know that I need to find the greatest common divisor of k and m. I'll see what that value is. So Let's do that now. Greatest common divisor of k, which is 2, and m, 14. That's 2. Now what that 2 tells me is that when I divide both sides by 2, I need to divide the modulus by 2. That's what the 2 tells me. If this was 1, you would just leave the modulus unchanged. You basically divide it by 1. Right, so dividing by 2, so 2n is congruent to 26 mod 14. So that's n is congruent to 13. And the 2 here tells me divide that by 2. So mod 7. Now the 2 here is also telling me that there's going to be 2 solutions to this mod 14 equation. So the first thing is change this into the least residue by taking off multiples of 7. So that will give me n is congruent to 6 under mod 7. But remember, the original equation was about mod 14. So we can go from 6 up to 14 by adding multiples of 7 until we get to 14. So I could say that the solutions are n is congruent to 6, add 7 to that, and 13 for this equation. Okay, so here we want to solve this equation. 42y is congruent to 168 mod 35. Now actually you may not or may not have spotted that actually 168 is a multiple of 42. So I can, if I want to, divide both sides by 42. So let me just write down k equals 42. You may not spot it's 42, you may find a smaller number, but you'll need to just carry on dividing it. But try and find the highest common factor of 42 and 168. That's 42. So I now want to find the greatest common divisor of k and m. That's 42 and 35. That is 7. So this is telling me that there are 7 solutions, and also I need to divide the mod by 7. So let's just write that down. 7 solutions. 7 solutions. Divide mod by 7. So let's do that. So we divide both sides by 42 because k is 42. So I'll have 42, so not 42y is congruent to 4 mod, and 35 divided by 7 is 5. Okay, this is actually the least residue answer for mod 5, but we can keep adding 5s until we go all the way up to 35 to find all the other solutions. So I'll write y, write solutions here, y congruent to 4 or 9, 14, 19, so I'm just adding 5s on, 24, 29, 34, and I'll stop there, and there are 1, 2, 3, 4, 5, 6, 7 solutions, as we said there was going to be. Okay, so this question here says find a multiplicative inverse of 10 modulo 63, hence find a solution to the equation. And the reason we're finding a multiplicative inverse is so that we can solve this equation here. Now, first of all, we need to find the greatest common divisor of 10 and 63, but we've got to use the Euclidean algorithm to do that, so that we can work backwards, so that we can write hopefully 1 equal to some multiples of 10 and 63 using Bezier's identities. We've got to work backwards, so we need to use the Euclidean algorithm first. So Euclidean algorithm, let's do that first. So remember what you do, you take the bigger number and you write it as a multiple of this number plus a remainder. So 63 equals 6 times 10 plus a remainder of 3. Then may remember that we take this number, the 10 and the 3, and they get moved across, and we carry out the algorithm again. So now we write 10 as 3 times by 3 plus 1. Okay, and again, these are the numbers that we move across. We're going to stop when there's no remainder. So 3 is equal to 1 times by 3 plus 0. So there's no remainder. So this is where we stop. Remember, you go back to the previous line, look at the remainder. That will tell you what the greatest common divisor of the two numbers is. So the greatest common divisor of 10 and 63 is 1, which is what we wanted. So now we're going to use identity and then work backwards so that we can write 1 as a multiple of 10 and 63. So the first thing we do is we go to this line of working here and we rearrange it so we can write 1 equals 10 minus 3 times 3. 1 equals 10 minus 3 times 3. Then we go to the previous line and we can replace this 3 here. We can replace it with 63 minus 6 times 10. So we'll write 1 equals 10 minus 3 times by, and in brackets we'll do 63 minus 6 times 10. Now remember, we want to simplify this, group things together as we go along rather than leave it to the end, because otherwise it's too messy, it's too difficult to do. So we've got a 10 there. Now when we multiply this out, we'll have plus 18 lots of 10 minus 3 minus 6. So 18 lots of 10 plus another 10 makes 19 lots of 10, and then minus 3 lots of 63. And then and that's it. We've completed the algorithm. So yeah, 1 can be written as 19 times 10 minus 3 times 63. And the multiplicative inverse is the number in front of A. Now A is this number here. So you're looking for this part, looking for the 10. And the number in front of it is the multiplicative inverse there, which is 19. So we'll just write down the multiplicative inverse of 10 modulo 63 is 19. So that's going to help us with part B when we want to solve this equation here, because what we're going to have to do is multiply both sides by the multiplicative inverse of 10 under mod 63, which is 19. So basically times both sides by 19. So you've got 10x is congruent to 4 mod 63. We times both sides by 19. So I'll have a 190x is congruent to 4 times 19. Let's just work that out. I think it's 76, I think. Yeah, 76 mod 63. So the mod doesn't change. And then the last step, what we need to do, because this is mod 63, we need to work out what the residues are, like the remainders. So if we took 63 away from 190 3 times, we end up with 1 or 1x or just x. If I take 63, just one lot of 63 away from 76, I end up with 13. So this would be my final solution. So I'm just going to put here what I've done here. So I've subtracted 3 times 63, because we're in modulo 63, it's just finding like the lowest residue, and then I've subtracted just 63 from here. Okay, so it's a nice little trick, this multiplicative inverse, because then it allows you to do this. It will always leave you with one lot of x left, because we've followed through this process here in reverse. Now, are there any other solutions? No, because if you add 63 to that, that's bigger than the modulus. So yeah, that would be our final solution. X is congruent to 13 under this mod 63. So in this question, we need to solve this modulus equation here. There are two methods. So the first method is just to, as the equation written, we can just find a multiplicative inverse from the numbers that are given. Okay, the advantages of that is you don't need to simplify. It might be slightly less work. The problem is that the numbers can be quite big when you're doing the Euclidean algorithm, and you're applying that backward as well, Bezout's identity. So the numbers can be quite big, and you're going to be backwards and forwards using a calculator. The other method is that we simplify it first and then find the multiplicative inverse. I'll just put that up there. Okay, the advantage is that numbers will be smaller to deal with, so you can probably do the arithmetic in your head. Numbers will be smaller. I suppose the disadvantage is you've got to simplify it first. So I'm going to use the method where I'm going to simplify it first. So if I'm going to simplify this, I need to look at the 75 and the 12 and think, what can I divide both sides of that by? Well, I know I can divide both sides by 3. So I want to find a greatest common divisor of 3 and 237. Now, 237 happens to be one less than 240. So I know that 3 goes into 240, so it goes into 237. We could add the digits up, couldn't we? 2 plus 3, 5, plus 7 is 12. 12 is divisible by 3, so this number must be divisible by 3. So the greatest common divisor is 3. Now what does that mean? That means that I need to divide the modulus by 3, and it tells me that there are 3 solutions. So dividing both sides by 3, I get 25x is congruent to 4, and I divide the modulus by 3. That's going to be 1 less than 80 times 3, so it's going to be mod 79. So that'd be my first step. So this is the actual equation I'm going to be solving, and use that then to find all the solutions to the original equation here. So now we need to find the multiplicative inverse of 25, because we're going to multiply both sides by a number so that it reduces down to just x. So the first thing that we need to do is find the greatest common divisor of, and remember it's these two numbers here, a and m, so 25 and 79. So I will use the Euclidean algorithm to do that. So starting with the bigger number 75, that can be written as 3 lots of 25, which is 75 plus a remainder of 4. Move these two numbers across, the 25 and the 4. So now I have 25 equals, how many 4s is that? 6 4s. 6 times 4 plus 1. Move these two across. So now I'll have 4 equals 1 times 4, or 4 times 1. Let's write it the other way around. 4 times 1 plus 0. So we stop, look to the previous line, and we find the greatest common divisor, which is 1. Okay, so the greatest common divisor of 25 and 79 is 1, which is what we wanted. So now we're going to apply Bezier's identity. So doing Bezier's identity, we can write, going back to this line here, 1 equal to 25 minus 6 times 4. So 1 equal to 25 minus 6 times 4. We go to the previous line, it's only going to be a couple of lines to do, and the 4 here will replace with 79 minus 3 times 25. So just underline that, that's going to get changed to minus 6 times by, and in brackets, 79 minus 3 times by 25. If I group them together, what do I have? Well, here I've got positive 18 lots of 25 plus another 25. So I've got 19 lots of 25 minus 6 lots of 79. Now, to help you remember which number you're looking for, we want the multiplicative inverse of 25. So you look at the number in front of the 25, that will tell you what it is. So we want to find a multiplicative inverse of this. What is it times by? It's times by 19. So the multiplicative inverse of 25 is 19. The multiplicative inverse of 25 is 19. So now I take my equation, 25x is congruent to 4 mod 79, and I times both sides by 19. I think I'll need a calculator for the 25 times by 19. That will give me, 25 times 19, 475. So 475x is congruent to 4 times 19, which is 76, I think. 76 in mod 79. So we now need to convert the mod 79s, convert the numbers to mod 79. So this is actually already in mod 79. If I took away 79 from that, it's going to end up being like -3, so that's fine. We'll leave that as it is. Let's think about how many lots of 79 we need to take away from that. So it should be 475, well 474 should be a multiple of 79. Let's just check. That's just right, it is. So if we take away 6 lots minus 6 lots of 79, that turns it into x. So we've got x is 76, which is one solution. Now let's look at the original equation. It's mod 237, so we can go all the way up to 237. So we can keep adding 79s onto this number to find the other solutions. So 76 plus 79, that's 155. And we said right at the start here, didn't we? We said there were 3 solutions. So let's add another 79 to that. And that's 234. So there we go. They would be our 3 solutions under modulus 79. Sorry, not modulus 79, modulus 237, because that's the original question, 237. Or you could just give the answer as 76 mod 79. So you need to give one or the other. So either x equals 76 mod 79, or these 3 numbers mod 237. You should now be able to do exercise 1E on pages 24 to 25 of the textbook. So a recap for this. So we can add or subtract things to both sides of our mod equation. No problem, we can just go ahead and do that. We need to give our solution as what we call the least residue. So the least residue is going to be positive, so it can be 0 or greater, and it's going to be less than or equal to, no, less than the modulus. It won't be equal to the modulus, so less than the modulus. If I have an equation in this form, AX is congruent to B in mod M, then if the greatest common divisor of A and M divides B, then its value gives us the number of solutions. If the greatest common divisor of A and M does not divide B, that tells us that there are no solutions. If we have an equation in the form where we can divide both sides by K, so let's say we've got something like this in mod M. If the greatest common divisor of K and M is 1, which basically means K and M are co-prime, we just divide by M, but leave them, divide by K, but leave the mod alone, leave mod. Whereas if the greatest common divisor of K and M is not equal to 1, let's call it a value of D, or I'll call it a value that we'll call D, then we still divide both sides by K, but we need to divide the mod by D. And sometimes we solve an equation by multiplying both sides by the multiplicative inverse. So there'll be equations of this form, just like in the second bullet point. The multiplicative inverse will only exist if the greatest common divisor of A and M equals 1, and we can show it equals 1 by using the Euclidean algorithm. And then once we've done the Euclidean algorithm, we can then write that greatest common divisor 1 equal to a multiple of A and M, and we'll call those multiples P and Q. So let's call that AP plus MQ. So that's Bezier's identity that we use, the Euclidean algorithm in reverse to do this. And this value P here is the multiplicative inverse. So P is the multiplicative inverse.